There's a difference between just reading to know something and preparing yourself for the actual presentation. So that's a little bit of encouragement for anyone who has been planning something and you want to know more and more, like you want to know deep about it. Yeah, so just making this presentation, preparing it, made me learn so much more. Yeah. So we'll begin. We have the overview. So database management systems are composed of mostly 5 main components. So the first component is the client communications manager. So as you can see, it establishes and remembers a connection state for a caller. So this will be any client that is calling the database. It also responds to the SQL commands from the caller and returns both data and control messages. These are the errors, the codes, all that. So the second one is the process manager. The process manager is a thread of computation that is assigned to the command or the query. So the process manager also determines whether processing should begin immediately or defer when resources are available. This is called admission control. So the third component is the relational query processor. So these are a set of modules that are responsible for passing this query that you've passed, and then they compile it into an internal query plan and then executes it. So there are other things that happen in this phase. For example, permission checks are made. For example, is the user allowed to run this query? Yeah. Number 4 is the transaction storage manager. So this one manages data access and manipulation calls. The storage system also includes algorithms and data structures for organizing data on disk. There are buffer mechanisms between the disk and memory. These mechanisms are also handled in this stage. The last one, number 5, is shared components and utilities. So these are utilities which are invoked during or independent of any transactions. They basically ensure full functioning of the database management system. An example is a memory manager. It is used whenever memory needs to be dynamically allocated or repassed. Another example is the system catalog. Yeah, so this is a diagram which shows the main components of a database management system. So there's the first process at the top, the second one, the third one, query passing and authorization, and the relational query processor, then you have the transactional storage manager, and the shared components and utilities. We'll go over each one of them, and we'll focus now on Postgres. So the first one, which is the client communications manager. As you see, Postgres uses a message-based protocol for communication between the front end and the back end. It is supported over TCP, IP, and Unix domain sockets. So in the startup phase, the front end opens a connection and authenticates the server. During normal operation, the front end sends queries and commands, and the back end returns the results and responses. The termination, most of the time, is closed by the front end, although the back end can force a close. We are all familiar with this. For example, when you open connections, most of the time the server is responsible for closing the connection, sometimes. So the client library, which implements, that is responsible for this, at the client communications manager level, is called libpq. Yeah, it's a C program, and it implements using the wire protocol. So for example, clients like PSQL have to incorporate libpq in their logic. Yeah, so we move we've established a connection. So the next thing now is looking at how the process is managed, how the resource is managed. So for example, once a client establishes a connection, the database management system has a worker which does work on behalf of the client. So your client maps to a database management worker, DBMS worker. So a 1:1 ratio exists between the client and the worker. So each connection is mapped to its process. So when this happens, a new OS process is forked and becomes the backend for that connection. This process model is called the process per worker model. So basically, each worker is assigned a process. This model is relatively easy to implement because the OS scheduler manages time sharing of the DBMS workers, and the system benefits from OS protection facilities. So the programmer doesn't have to worry about things like memory overruns because the OS, this is managed at the OS level. The drawback to this model is that processes need to share data structures. For example, the global log table, the buffer pool, all of these need to be shared across all these connections. So this is one of the drawbacks to this model. So the solution to this is to explicitly allocate these shared structures across all these processes. So this is done. This is done by you have the shared buffers, which is the shared memory. It's in Postgres, it's called the shared buffer. Yeah. So every worker process is made aware of the shared memory regions at startup. So while this process is spawning, it has to be made aware of the shared buffers. These are all the shared. It's a data structure where you access the shared memory. Processes usually consume more memory than threads, and as you can see, this model uses processes. So with processes, context switching is usually expensive. So the result is that Postgres usually scales poorly under many concurrent connections. So one way you can be able to ensure that it doesn't scale poorly is by having connection poolers. So many of us have heard about PG Bouncer. It's a connection pooler. So it fixes this memory overhead by maintaining a small pool of persistent connections and routing requests through them. This eliminates the need to spin up new processes by every client. Yes, so having a connection pooler is really important for your Postgres setup. So the next stage, we've spawned a process, so now we go to the query processor. So this is where the query is processed. Several things happen here. There's the validation, optimization, it's being passed, and then it's the execution phase. So yeah, it does all that. So there are several stages here. So the first stage is the parser stage, which validates the query syntax. So it has several files. The Postgres, at the code level, there are several files which are called to validate the query syntax of the query that's been passed. So you have the grammar files. The grammar, it's a grammar file and an Excel file. The output of this process is a parse tree. A parse tree is basically in machine understandable form. It's the query now, but in machine understandable format. Here, it also performs semantic interpretation. So it resolves table names, column types, functions, and operators. using system catalogs. So it gives it a semantic meaning. Checking whether these column types exist, functions and operators, table names. So the next stage is a query rewrite rule system. This is how it's called in the Postgres. So it rewrites and normalizes the query without changing semantics. So it applies rules, for example, expanding views into underlying tables, and applies custom rewrite rules. So an example is, for example, views. Views are saved queries. So, for example, you might have a view which is responsible for returning validated users. So you create that view by statement create view validated users as select star from users, select ID from users where activated equals to true. But so every time this view is called, the query rewrite rule system is responsible for interpreting it into its complete meaning, if I can use that one. So, for example, if you do something like select star from validated users, which is a view, now this rewrite goes and checks what this saved query, the complete meaning, and then it rewrites it to it. So the next step is after rewriting the rule, now it still has the same semantic meaning. Now the next step is the planner or the optimizer stage. So for every query, you might have several execution plans. But now this stage, the optimizer stage is responsible for giving you the most optimal plan. So it creates an optimal execution plan for many possible ways to execute a query. So it examines feasible alternatives and selects the plan expected to run the fastest. So the output of the planner is a tree of plan nodes. So we are getting into more familiar territory now. So when you run explain analyze on a query, what you usually see is this tree of plan nodes. And each node is usually an operator. So you have the types of plan nodes. You have scan nodes. These ones are responsible for fetching the data. For example, the sequential scan, the index scan, bitmap hit scan. And another type of a plan node is the join nodes. An example is the nested loop or merge join, the hash node. And then you have the auxiliary nodes, which, for example, the sorts, the aggregates, and the limits. So these ones, you usually see them when you run explain. When you run a query with explain, you'll see this tree of plan nodes. So it displays the query plan, the reference tables, the scan methods, and join algorithms, if there are multiple tables being referenced. So when you run explain with analyze, it usually executes the query and shows runtime statistics. So the next stage is the executor stage. Now the executor stage is responsible for executing. You have the plan, so the executor just executes. So the executor takes the plan from the planner and recursively processes it to extract rows. It's usually a demand pull pipeline mechanism. So each time a plan node is called, it delivers one or more rows or reports completion. It says, I'm done giving you rows. So each one of these operators, for example, the operator could be a sequential scan. So the sequential scan will receive a tuples, will process them, and will emit them. And each operator usually exposes a function, like get next to fetch the next tuple. So this model is called the volcano model. where you have each node in the tree is an iterator. So iterators usually combine data flow with control flow. So the get next function, which has been called at the operator level, it returns a tuple reference, call stack, and also it returns control. So only one process is needed for sequential execution. Also, what happens when you have parallel query execution? Because the planner might determine that this query takes a lot of resources, so it might come up with a plan that will need parallel execution. So in this model, what really happens is that each worker runs its own iterator pipeline. So you have a leader process which pulls results from each of the workers. And when you run explain analyze and you see something like gather or gather much somewhere there in the plan, this is how you know that there's some parallel query execution. So each of these workers has exactly one child plan, and the portion is executed in parallel. So the next thing is memory allocation. So in this whole process of fetching data, this at the executor process, we've not discussed how memory is allocated and how is this data, how are these rows moving. So here you have to take note of three things. The first thing is the tuple descriptors. So this is an array of column references, which each of them usually has a reference, the tuple in memory, and the column offset within that tuple. And each iterator is pre-allocated a fixed number of these. So in this iterator model, not tuples are passed along, but tuple descriptors, which are references, they don't pass tuples, they just pass references to the tuples in memory. Another thing you should be aware of is the buffer pool. So the buffer pool is where the actual tuples are stored. The other thing is workman. Workman is a configuration setting. So the thing that it does is it determines memory allocated per operation before spilling to temporary disk files. So this is mostly used during sorts or hash tables or aggregates. And I think the default is usually 4 MB. But one has to be careful here. So if you have multiple sort/hash operations which are running concurrently across many transactions, setting workman too high can cause memory exhaustion. So this is because, for example, you have a plan which has like 4 sort operations or hash operations. This is going to it will be expensive for you if you're running a heavy query which is fetching a lot of data. And yes, if you're running a heavy query which is fetching a lot of data, it will be expensive for you because you have to multiply each of these sorts and the configuration in the workman. So this can end up causing too much memory exhaustion. We move to the next component, which is the transactional storage manager. So every database management system has to control where data is being placed and when. So the first one is controlling storage in space or spatial control. So Postgres usually uses standard OS file system utilities to do this. It creates a file in the OS file system and manages the positioning of data and offsets within that file. So the OS file system sits between the applications and the disk and maps high-level operations to low-level disk block reads and writes on the physical device. With Postgres, the most favored file systems is, you have two. The first one is ext4 and XFS. ext4 is simple and stable. XFS is highly performant, and especially for large-scale workloads. But the problem with this one is that it requires significant tuning. So let me so the second part of it is controlling when to write data to disk. So this is the temporal control. So every DBMS usually has logic to handle the writes to the device, to the disk. So here you have the buffer pool, which are the shared buffers. This one usually loads disk pages and uses them directly in the native format and later writes them to the disk. So this one is in the memory. And you have the log tail or the while buffer. So this one is an in-memory queue which stores generated log entries, and it corresponds to the while file on the disk. And the while file is periodically flashed to the disk. Sometimes during when you're committing, when a commit request has been made. The benefit of while write-ahead logging is that it significantly reduces disk writes, because only the while file needs to be flashed to guarantee a transaction is committed, rather than every data file being changed by the commit. So we are wrapping up. So the last part in the transactional storage manager component is concurrency, control, and recovery. Most of us are aware of the ACID properties. So Postgres is ACID compliant, atomicity, consistency, it offers isolation, and durability. So another concept is that of serializability. Serializability, it relates to the correctness of concurrent transactions. So you might be having several transactions that are competing for resources, and they are all committing. So how do you ensure correctness in such a scenario? So Postgres handles this via a protocol called multi-version concurrency control, MPCC. So in this protocol, the transactions do not hold locks, but are guaranteed a consistent view of the database at a particular time, at a fixed point in time. So it uses multiple versions of a row of a logical table to ensure that the client always has a consistent view of data. So the key takeaway here is that reads don't block writes and writes don't block reads. But cleanup or garbage collection is needed regularly so as to be able to remove the stale raw versions. So just to illustrate, for example, when you're doing an update, it doesn't go and replace. For example, if you want to update a row from 5 to 10, it doesn't just go and replace directly. That's not how Postgres works. It has versions of that row. So it marks the first row as stale, and then it creates a new row. Yeah, and then it marks the old row as stale. Yeah, so there are several anomalies which you need to avoid when you're handling multiple transactions that are committed. So you need to avoid dirty reads, you need to avoid non-repeatable reads and phantom reads. Dirty read is when a transaction reads data written by a concurrent, uncommitted transaction. Yeah, the rest of the definitions. So what does Postgres offer? What are the isolation levels that are offered by Postgres? So Postgres offers read committed, and in read committed isolation levels, read committed is usually the default isolation level in Postgres. So in read committed, reads can only see committed data before the query began. And when you read, it doesn't see in-flight data, or it doesn't see data that is yet to be committed by concurrent transactions during the execution. So when you run two successive select statements, they can see different data, even within the same transaction. If that is, if other transactions commit changes between the two reads. The second isolation level is called serializable. Serializable is the strictest isolation level, and it emulates serial transaction execution. So it behaves as if these two transactions have executed serially. Transaction 1 first finishes, and then transaction 2 completes. So, however, applications must be prepared to retry transactions once they are aborted, because select queries see only data committed before the transaction began. So uncommitted data or changes committed by concurrent transactions during execution, it cannot see them. So for example, during an update, you have transaction 1 trying to update and transaction 2 trying to update. So the second transaction has to wait for the first transaction to commit or roll back. So if the first transaction rolls back, then the waiting transaction, if the first transaction rolls back, then the second transaction, the second transaction which is waiting, it proceeds to change the role. But if the first transaction commits, if it commits, the second transaction has to re-execute and check whether so this is serializable. So if the first one commits, the second one returns with an error. It returns with an error and say it couldn't update because of serial error. So under the hood, this serializable isolation level runs using a technique called serializable snapshot isolation. It's exciting stuff, but it's quite complex. Yeah. So the last section is shared components. Shared components. The first one is the system catalog. This is where the DBMS stores the schema metadata, such as information about tables and columns and internal bookkeeping information. In Postgres, the system catalogs are regular tables, and normally you should not change the system catalogs by hand. It will run into trouble. It usually accessed via the PG catalogs. And then you have the memory manager, which allocates memory with memory context. It uses something called memory context, which provides a convenient method of managing allocations made in many different places that need to live for differing amounts of time. That's it for my presentation.
Good afternoon, everybody. Daniel has given us so much to think about, right? He has told us so much about Postgres, and we have an inside joke. I call him Mr. Postgres because he's so passionate about Postgres. So yeah, thank you for your talk. Does anyone have a question for him?
Thank you for that nice presentation. My question is on the last section on isolation levels. How do you pick the correct isolation level? What informs your choice so as to ensure that there is that balance between performance and ensuring that data is consistent? Thank you.
Okay, good question. So the default isolation level in Postgres is the read committed isolation level. So of all the anomalies, it prevents dirty reads. The committed, the read committed. Of all the anomalies, remember we discussed the three anomalies. You have the dirty read, the non-repeatable read, and the phantom read. So the default one usually prevents dirty reads. But with it, there is a possibility of non-repeatable read and phantom reads. But for most applications, it's usually okay to run with this isolation level. But the other one, because in Postgres we have two, we have read committed and we have serializable. So for example, if you're running a banking software and you're running Postgres, you have no excuse for experiencing all these anomalies. For example, non-repeatable read or phantom read. So you have to ensure that you put to serializable. I hope I've answered the question. So really it depends with the application you have. If you're running a bank, you are susceptible to some of these anomalies, the non-repeatable read and the phantom read. So you need to ensure that you use serializable.